video, I would like to go through the second section of 10.8 on procedures in your book that is entitled Using More Registers. But first I want to go through, this is the sample that I walked you through in the previous video. And right here, starting on line 58, is the code for the function. If you recall here, we're only using, I'm going to highlight it, registers S0 and S1 as our working registers inside the function, and we're assuming that those two registers are available to use. So now if you go over to your book, the difference in this section is that let's assume that you need far more registers. Let's say, for example, you have a program, and in the main portion of your program, you're using registers S0 through S7 for whatever have you, maybe some calculation instructions, and each of those registers has a value assigned to it right now. Now let's say you call a function, and inside that function you're going to be performing more calculations. So what registers do you use? If they're all occupied, S0 through S7 are occupied, and you need that data after the function call, you can't just use them inside your function because you will overwrite whatever's in there. So the idea here is to take the values that are in S0 through S7, store them in memory, call your function, do whatever you need to do, and then right before you return to main, restore those values from memory back into the registers that they were originally in, so you can continue. So the data structure that your book proposes you use to store those register values is a stack. And a stack is simply a data structure that stacks values one on top of the other. So literally picture a data item on top of another data item. So how do you know where one ends and one begins? You know that each data item in memory is allocated a certain number of bytes. So let's say, for example, we're using a dot word. That's 4 bytes, right? So you could find the end of one data item and the beginning of the next by using your understanding of how much space is allocated for each data item. What we use to track the address is a stack pointer. So you'll start by counting from 0, and then you just add 4 bytes and then another 4 bytes, etc., until you get to whichever element you want inside your stack. The terms we use: pushing, adding elements onto your stack, so you push onto the stack, and you pop when you remove items from the stack. So basically, if you look at the diagram that's in your book, it does a good job of kind of helping you visualize, right? Here are the contents of the stack. Remember, this is main memory. And here is your pointer, and your pointer, again, is an address. So the register holding the pointer address is SP for stack pointer. This example here in your book is assembly code for this procedure here in C++. So the procedure, you can see, accepts 4 parameter values, performs some arithmetic, and then returns the answer. And you know that this one statement here, F equals blah, 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 that cannot be done in one statement in assembly. You need to perform this as a separate statement from this, as a separate statement from this whole thing. So that's why this is a good example for why you need multiple registers. Now, take a look at the assembly code. The very first statement, and a very, very important item, is to make room on the stack. So how do you know how much room to make? You need to store values for, in this scenario, and for this example, it's registers T1, T0, and S0. That's 3 values, 3 word size values. One word is 4 bytes. 4 times 3 is 12. So you're going to make room by subtracting 12 from the current address. So by subtracting 12, you're moving your pointer down to allocate space for 3 items. Now, store each of the items from the register to the location in the stack. Why are these 0, 4, and 8? That's the disposition. So we start with the pointer down at 0. Add 4 to that. You're then at the start of position 4, byte 4 for the next word. Add 4 to that. You start at 8, and you'll end at 12. So these are the 3 statements that take the values from the registers, put them into memory. Now you can go ahead and perform this task here. That's what these 3 statements are doing. And then in this next statement, add S0 to V0. This is moving the final answer. S0 is holding the value for F. That's moving it into V0 so that it can be passed back to main. Now that you're all done with this right here, you can then load all the values from the stack back to their original registers. So the order in which you do this is important because at position 0, that's where S0 starts. So you want to make sure that goes back to S0. At position 4, that's where T0 starts. Position 8 is where T1's value starts. Okay, so that is how to move everything back. And then the very last statement adds 12 to the stack pointer. So that restores the stack pointer back to its original point. So you subtracted 12, and then when you were all done, you added 12 bytes back. Okay, so you're back essentially at ground zero, if you will. Now you can jump return back to your calling program.